students, myself Muhammad Adil Sheikh, Assistant Professor of Chemical Engineering Department from LJ Institute of Engineering and Technology. So today we will talk about process equipment designing, under which Venturi scrubber. We will talk about Venturi scrubber and its process designing steps and one example related to it. So let us start with the Venturi scrubber. Now, Venturi scrubber is normally preferred for removing particulate matter from the gas stream, and it provides efficient contact between gas and a liquid. In Venturi scrubber, as you can see, both gas and a liquid will flow in a co-current manner. The gas flows in a throat of a Venturi along the spray of absorbing liquid into the converging duct. So, when the gas and liquid will flow through this throat of the Venturi, the particulate matter from the gas is absorbed by the liquid, and so we can get a clean gas outlet and also the drainage from the bottom of the Venturi scrubber. Now, the Venturi scrubber requires higher power consumption and also provides large gas and liquid side pressure drop, which are the disadvantages of the Venturi scrubber. Now, it provides a co-current contact between gas and a liquid. Now, spray chamber cannot remove very fine particles below 10 micrometer size, but the Venturi scrubber can remove fine particles up to 2 micrometer size very effectively. Now, we will see the process design of a Venturi scrubber. So, the first point is the fractional solute removal for a dilute system in a Venturi scrubber is given by the following equation, that is y1 minus y2 upon y1, which is equals to eta into 1 minus mx2 by y2 upon 1 plus mgm upon lm. Now the terms used are y2 is a mole fraction of a solute in a gas phase at outlet, y1 is a mole fraction of a solute in a gas phase at an inlet, where m is a slope of equilibrium curve, x2 is a mole fraction of a solute in incoming gas, gm is a molar gas phase velocity, lm is a molar liquid phase velocity, where eta is a mass transfer efficiency, which can be calculated by the equation that eta is equals to 1 minus e raised to minus ng. Now ng is a number of overall gas phase mass transfer units. So we can use the equation for the ng, that is number of overall gas phase mass transfer unit, as kg into A into RT upon PT into theta C. So the terms used are kg into A, that overall volumetric gas phase mass transfer coefficient for a dilute system, R is the ideal gas constant, T is operating temperature of a gas, theta C is a effective liquid gas liquid contact time, and PT is a pressure. Now the number of overall gas phase mass transfer unit for the Venturi scrubber should be between 1 to 2 for an efficient design. The liquid to gas ratio for a Venturi scrubber is in between 0.7 to 2.7 liter per meter cube, and the throat velocity should be kept in between 60 to 150 meter per second. The pressure drop across the Venturi scrubber can be calculated by the following equation, that delta P is equals to 2.584 multiplied by 10 to the power minus 3 into Vg square rho g ATH raised to 0.133 into L dash upon G dash raised to 0.78. So we will get the pressure drop in centimeter of water column. Now Vg is gas velocity in a throat in meter per second, rho g is a gas density in kg per meter cube, ATH is a Venturi throat area in centimeter square, and L dash upon G dash is liquid to gas ratio in liter per meter cube. Okay, so now we will see the example of a Venturi scrubber. So the question is to absorb SO2 gas from the exit stream of a boiler flue gas by using 1% of lime solution. And the data for the scrubber are given as follows, that volumetric flow rate of a exit gas stream is 24,000 meter cube per hour at normal conditions. Discharge pressure of a gas from the Venturi is atmospheric. Temperature of a gaseous mixture is 90 degrees Celsius. SO2 concentration in boiler flue gases is 4000 ppm. Solvent to gas ratio is 1.4 liter per meter cube. Throat velocity at the gas phase is 100 meter per second, and average molar mass of a flue gas is 29.48 kg per kilomole. So we will start with the answer. First of all, we will find out volumetric flow rate of a gas at an actual operating condition. So the QV is equals to 24,000, that is at normal conditions. So 24,000 divided by 273 multiplied by 273 plus 90, that is temperature. So we will get the answer is 31,912.1 in meter cube per hour. So if we convert it to meter cube per second, we will get 8.8645 meter cube per second. After this, we will find out inside diameter of a throat, that is di is equals to under root of 4 into 8.8645 upon 100 into pi. So the answer will be 0.336 in meter. The flow rate of a solvent is 1.4 into QE, that is volumetric flow rate of a gas. So 1.4 into 8.8645, that is equals to 12.41 liter per second. So if we convert in a meter cube per hour, it will be 44.677. Now the density of a lime 1% lime solution is 1012.5 kg per meter cube. So the mass flow rate of a solution will be 1012.5 multiplied by 44.677, that is flow rate of a solvent. That will be equal to 45,235.46 kg per hour. So if we convert into kg per second, it will be 12.565. Now we will calculate mass flow rate of a liquid, that is Lm, which is equals to 12.565 upon 1 upon 0.99 upon 18, that is for the water, plus 0.01 upon 74 for the lime. So we will get the mass flow rate of a liquid as a 0.693 kilomole per second. Now the mass flow rate of a gas Gm is equals to P into QV upon RT. So P is atmospheric pressure 1 into QV at 0.8645 that we have calculated earlier. R is a 0.082 multiplied by 273 plus 90, that is temperature 90 degrees Celsius. So we have converted into Kelvin, and so the mass flow rate of a gas will be 0.2978 kilomole per second. Now we are assuming Ng is equals to 1, as we have talked earlier that the Ng should be between range of 1 to 2. So the mass transfer efficiency will be eta is equals to 1 minus e raised to minus Ng. So we will get the answer of eta as 0.6321. Now fractional solute removal, that y1 minus y2 upon y1 is equals to eta into 1 minus mx2 by y2 upon 1 plus m g dash m upon l dash m. So now we require g dash m by l dash m, that is gm by flow area upon lm by flow area, so which is ultimately gm upon lm, and we are having values of gm and lm both, so we can get the answer as 0.43. x2 is equals to 0 because of pure solvent. We don't know what is the value of y2, so we will find it out. Now y1 is given in a question, that 4000 ppm, so we will convert it and we will get 0.004. The partial pressure of SO2 in a gas phase is 0.004 multiplied by 760, so it will be converted into 3.04 torr. Now we will assume the average temperature of a scrubber as 50 degrees Celsius. Equilibrium mass of SO2 per 100 mass of H2O is given as 0.035 in a question. So the equilibrium mass fraction will be 3.5 into 10 to the power minus 4. So its equilibrium mole fraction will be Xe, that is equals to the equilibrium mass fraction of SO2 divided by its molecular weight, and entire divided by equilibrium mass fraction of SO2 per molecular weight of SO2 plus the equilibrium mass fraction for water divided by molecular weight of water. So we will get the equilibrium mole fraction Xe is a 9.846 multiplied by 10 to minus 5. Now Ye is equals to Y1, that is 0.004. So we will get the slope of equilibrium curve Ye upon Xe. The m will be 40.63. So we are having all the values. Now we will put above, and we will get the value of Y2, that is 0.00386. Okay, so here only presence of 1% lime is there in a solution, and so the chemical reaction between lime and SO2 is not considered here. Now the pressure drop that is required in the Venturi scrubber is obtained from this equation, that is 2.584 multiplied by 10 to the power minus 3 Vg square rho g into ATH raised to 0.133 into L dash upon G dash raised to 0.78. Vg is given as 100 meter per second. ATH is a pi by 4 dei square. The dei we have calculated earlier, so it is 886.7 centimeter square. Rho g is Pm by RT, so 1 atmospheric pressure, molecular weight is given in a question, and we will get the rho g as a 0.99 kg per meter cube. Then L dash upon G dash is also given in the question, that is 1.4. So we will put all the values of this, and we will get the pressure drop of venturi scrubber as 82 centimeter of water column. If we convert into mm of water column, it will be 820. Okay, so that's it for the today's lecture. I hope you all have understood this. Thank you.